Hello everyone. Today we are going to go over our statistical analysis and related things relating to the Boeing 737 MAX crashes. Our agenda today involves going over the technical issue at hand, statistical analysis, the potential results and their implications, recommendations based on the analysis, and limitations and assumptions. Let's begin by going over the technical issue at hand. Over recent years, Boeing 737 crashes have increased significantly, garnering media attention and concerns about the reliability of aircraft systems in these planes. Boeing's Maneuvering Characteristics Augmentation System, or MCAS, has been named the culprit for many of these crashes. It is a system designed to prevent engine stalls by autonomously adjusting the aircraft's pitch. This is done on the angle of attack sensors within the plane. However, if these sensors are damaged or collect incorrect data, the system can make incorrect adjustments, leading the plane to nosedive. In some scenarios, pilots are unable to override the system, and this in turn can lead to a crash. The key issue is the dependency on a single sensor to make decisions. This dependency is dangerous to passengers as incorrect readings can cause catastrophic failures, as the incorrect reading can actually work to the opposite means, causing the plane to stall. To quantify the probability of a system failure, our team will utilize binomial distribution and tree diagrams. Through these methods, we can analyze and visualize any patterns that may occur, allowing us to provide a way for the MCAS system to be improved for higher reliability and prevent future failures. Now we'll deal with our statistical analysis. In the statistical analysis, one of the things we did was do binomial distributions. We know that there were two crashes, one on October 29, 2018, and the other on March 10, 2019. And there are about 19 weeks in that time frame. And according to the New York Times, there are about 8,600 flights per week. So the total number of flights might be about 163,400 flights. This leads to a probability rate relating to the flights of 2 over 163,400, which is about 0.00122%. The chart and table show the binomial distribution showing the respective probabilities of the amount of failures. There were also potentially 400 planes in operation, which may lead to a probability rate of about 2 over 400, which is equal to 0.5%. The table and chart are similar to the previous ones. Both of the results show that it is more likely for there to be one failure than it is for there to be zero. And this holds true for 2 failures and 3 failures compared to 0. Adding all the probabilities between 1 and 3 would be greater than 0 by itself. It would be about 0.13622 for 0 and 0.72208 for the sum of 1 through 3 for the flights, and 0.13466 for 0 and 0.72292 for the sum 1 through 3 for the planes. Now we move on to conditional probabilities.
Another of the methods used in statistical analysis was to use fault tree diagrams and conditional probability. In reports of the crashes, it was revealed that only one of the 2 area of attack sensors was being used to detect aircraft stall. Because of this, when a sensor would receive an error reading, the Maneuvering Characteristics Augmentation System would activate and result in the plane crashing. With the use of the diagrams, we used conditional probability equations to determine how likely it was for the use of only one area of attack sensor to result in the plane crashing. The equation came out to be the probability of failure is equal to the probability of the first sensor receiving an error reading plus the probability of the second sensor receiving an error reading minus the probability of the first sensor times the probability of the second sensor. Now let's assume that the probability of each sensor receiving an error reading is 0.01. Plugging that number into the equation gives us about a 0.02 probability of failure, which is quite high, especially when compared to the probability of failure when both sensors are used, which is shown by the equation equaling the probability of the first sensor receiving an error reading times the second sensor receiving an error reading. And once again, using that probability of 0.01 for the probability of sensors receiving an error reading, the probability of failure comes out to be 0.0001, which shows the use of both sensors is vastly less likely to result in the plane crashing.
So as for the potential results and their implications, using both binomial distribution along with tree diagrams will help us quantify failure probability a lot more accurately. And throughout the development of the 737 MAX, this implies many different things. Those results imply many different things. For example, let's say that if you were to apply a threshold in probability, whenever maintenance services might be necessary, they would be detected a lot more frequently, and reliability levels would increase across the board. In addition, in the development of the 737 MAX, a major fault that Boeing made was the fact that they didn't train the pilots on the MCAS system and how it operated at all, because they wanted to cut down on costs. And this significantly increases risk because they had no idea on how to disable the system whenever it was activated. They had no idea how to disable it. So if they would have utilized binomial distribution, they would have seen just how much the risk would have raised based off of the failure probability by itself. So that would have significantly made a difference. And using tree diagrams, in addition with that, will help interpret. The whole purpose of tree diagrams is to help interpret different situations in a very straightforward manner and simultaneously. For example, in a situation where the left sensor would have failed versus the right sensor failing, you would see how the failure probability will change. And using binomial distribution along with tree diagrams just helps make accurate future predictions, as well as just ensuring that all the methods are tied together in a very straightforward and easy to interpret way. So,
as for our recommendations based on the analysis, multiple angle of attack sensors should be used for the MCAS. At least 4 sensors are needed to reduce the chances of failure, since it is much less likely for there to be 4 failures compared to between 0 and 3 failures. Though ideally, there should be even more sensors used as a basic safety precaution. Also, the pilot should be trained on how the MCAS system works and what to do if the system starts to have issues, such as those that developed right before the 2 crashes. The limitations and assumptions of our analysis are that the 2 Boeing 737 MAX crashes were mainly caused by the MCAS failing, and that there could potentially be more design flaws with the 737 MAX that, along with the MCAS, will make the aircraft more likely to crash.
Future relevance. This project is connected to our future careers as engineers, most importantly in terms of safety. With these recent accidents of the Boeing 737, it becomes an unforgettable learning lesson for all involved with the development and design of the aircraft, and even for all engineers worldwide. While the Boeing executives are mainly to blame for not informing the pilots of major system changes, the MCAS system itself was incredibly flawed to begin with. Relying solely on one angle of attack sensor, it had a single point of failure with no backup. This becomes relevant for future projects, as building redundancy into our systems is extremely important for ensuring safety and reliability. With these backups or safeties in place, it is possible to prevent the worst outcomes from occurring. As future engineers, we should follow this rule and avoid designing projects without inbuilt redundancies. Applying the previously discussed statistical methods in the previous slides would allow us to measure and quantify the safety of systems such as the MCAS. Accurately finding these possible faults and retrieving this data for future analysis using statistical methods allows us to make calls on reliability. As such, engineers must place safety at the forefront of their designs when working on their projects.
In this presentation, we went over the Boeing 737 MAX crashes. The technical issue at hand mentioned the crashes, how the MCAS caused them, and the key issue being that the MCAS was dependent on only one angle of attack sensor. The statistical analysis with binomial distributions and tree diagrams show how it is more likely for 1 to 3 failures to occur than for 0 failures to occur, and that both sensors being active reduces the overall failure probability compared to only having one sensor active. The potential results and the implications mention how binomial distribution and tree diagrams play important roles in quantifying the failure probability and its implications throughout the airplane's development stages. Binomial distribution might imply that pilot training reasons are necessary based on the failure probability. Recommendations based on the analysis has the recommendations of multiple sensors being used, and that the pilots are trained on the MCAS and what to do when the system begins to have issues similar to the ones that occurred right before the 2 crashes. limitations and assumptions mentioned, the two crashes mainly being caused by the MCAS failing, and that there could be more design flaws that make the aircraft more likely to crash.